The derivatives of inverse trig functions come in pairs, much like the derivatives of trig functions sort of come in pairs. You know, sine is cosine and cosine is negative sine, that they go together. One of the things about trig functions is that anything that's a cosine, cosecant, cotangent, what do you always know about its derivative? It's negative. And the same is true for inverse trig functions as well, so that's kind of a nice rule to fall back on. Most of these are just something to memorize. There are proofs for them, and they rely on geometry and the Pythagorean theorem and some inverse trig properties. We're not going to prove those right now today, so I'm just going to tell you what they are. Okay? So what I'd like to do is just sort of compare and contrast the function itself with its derivative. And I'd like to kind of make 4 columns so that we can sort of see the mirroring that's going on where you have some similarities. So let me see what I would like to do here. See if this will work. And then I'll try this. No, too quick. Okay. Okay, if the function is the inverse of sine, and we'll say of a. Let's stay away from x, but we'll use a. Its derivative is a prime over 1 minus a squared. The a prime is the chain rule. Sometimes you'll see it taught like this. You'll see it as 1 over, and then like the a prime comes over here as the chain rule part. So 1 over this, and then do the chain rule on the end. But ultimately the a prime ends up in the numerator. So I don't really care how you want to write that. If you want to write it as 1 over and then put the chain rule on the end, or if you want to write it with the chain rule in the numerator. But the same thing is true, or it's very similar, for the inverse of cosine. Its derivative is the exact same, just with a negative sign. And so the derivative of that would be, you could write it like negative 1 over the square root of 1 minus a squared, and then tack a prime onto the end, or you could put a prime in your numerator. It's really up to you, your personal preference, however you want to memorize that. So the pattern to all of these is as follows. All of the derivatives are 1 over with a chain rule. So we're going to do inverse tangent. We're going to do inverse secant. So it's always 1 over times the chain rule. And then all the cos are going to be negative 1 over something times the chain rule. So that's where the similarities are. It's always a fraction. It's always multiplied, or always divided by something, and then always multiplied by the chain rule. So then let's do the other patterns. Let's do secant and cosecant. So the inverse secant of a has a derivative that also has a square root. Its derivative is as follows. The square root is also in the denominator. The order is reversed. A squared minus 1 instead of 1 minus a squared. And there's the absolute value of a out front. That's the strangest one of all of them. And again, that comes from the Pythagorean theorem and solving SOHCAHTOA and doing SOHCAHTOA backwards and finding the derivatives. And so then inverse cosecant of a would be the same, it's just with a negative 1. So you'll have the square root of a squared minus 1, and the absolute value of a out front. And then finally, tangent and cotangent. These are the easiest ones, I think. Tangent of a doesn't have a square root at all because it doesn't involve a hypotenuse. The other ones, sine and secant, both involve a hypotenuse because they're part of so and ka. TOA doesn't involve a hypotenuse, and so it's an easier fraction, and it's the fraction a squared plus 1 without the square root. And so then cotangent would be negative a squared plus 1, and then the chain rule. All right, so those are the 6 derivatives. So you're just going to use these, not in any word problems. You're just going to do some applications of these in terms of finding maybe a tangent line. So let's do one example of these together just as you may see it. You're going to be doing the same thing. You'll be answering velocity questions, acceleration questions, tangent line questions, normal line questions. The questions don't change, it's the functions that change. And so let's do a normal line, bless you. Normal line to the function y equals the inverse secant of 2x. And let's do that at an x value of 1. So as with any normal line, we need to find the point, and we need to find its slope. And so we've got the x-coordinate of the point. The y value of the point is going to come when we plug 1 into the function. So it'll be 1 times the inverse secant of 2. If you remember your rules about inverse functions, the secant inverse of 2 is equivalent to the cosine inverse of half. And that's one of my favorite things to do in inverse functions, is to change it from secant, which I'm not as familiar with, back to cosine, which I am, using the reciprocal rules. So remember, there's an inverse and there's a reciprocal. Those are not the same things, but they are related to each other. So the secant is the inverse, and the 2 is the reciprocal part. And so then I want the cosine inverse of half. There are multiple answers to that on a unit circle, but we go with the domain that includes the first quadrant, and so that would be pi thirds. And so my point value is 1 comma pi thirds. That's my point. Then I want to do the slope, and I'll do the slope using the derivative rules that I gave you, so that would be y prime. This will be 1 over, and the rule for secant has a square root in it. It'll have 2x as the quantity squared minus 1, and it'll have the absolute value of 2x on the outside. And what else do I have to remember that's going to be a deal breaker for like a multiple choice question? The chain rule. And so this would be multiplied by 2. And so on a multiple choice, that could be the difference between the right slope and the wrong slope. So now I'll plug the number 1 into this. So I'll get 2 as my numerator over the absolute value of 2, which of course is positive. And then over plugging 1 in, I'm going to get 4 minus 1. So I end up with 2 over the absolute value of 2, which is 2, and rad 3. So I end up with 1 over rad 3. Nope, no rationalizing needed, especially because I'm going to be making this normal. Okay, and the normal is going to take 1 over rad 3 and make it, what? Negative rad 3. And so my normal line will just become y minus the y value of pi thirds the normal slope of negative rad 3, and x minus 1, which you do not need to distribute or simplify. Some of you did on your quiz, and then I got to get my work out, and then I got to make sure you did the work right. But you don't have to. You can just leave that in its point slope form, and that would be the normal line.